Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 4, Harmonic Constructions and the Fundamental Theorem of Projective Geometry. Section 35, the Fundamental Theorem of Projectivity. It has been shown in Chapter 3 that any three distinct elements of a one-dimensional form may be made to correspond to any three distinct points of a line by a projective transformation. Likewise, any four elements of a two-dimensional form, no three of which belong to the same one-dimensional form, may be made to correspond to the vertices of a complete planar quadrangle by a projective transformation. And any five elements of a three-dimensional form, no four of which belong to the same two-dimensional form, may be made to correspond to five vertices of a complete spatial five-point by a projective transformation. These transformations are of the utmost importance. Indeed, it is the principal object of projective geometry to discover those properties of figures which remain invariant when the figures are subjected to projective transformations. The question now naturally arises, is it possible to transform any four elements of a one-dimensional form into any four elements of another one-dimensional form? This question must be answered in the negative, since a harmonic set must always correspond to a harmonic set. The question then arises whether or not a projective correspondence between one-dimensional forms is completely determined when three pairs of homologous elements are given. A partial answer to this fundamental question is given in the next theorem. Lemma 1. If a projectivity leaves three distinct points of a line fixed, it leaves fixed every point of the linear net defined by these points. This follows at once from the fact that if three points are left invariant by a projectivity, the harmonic conjugate of any one of these points with respect to the other two must also be left invariant by the projectivity. Theorems 2 and 3 corollary. The projectivity in question must therefore leave invariant every point harmonically related to the three given points. Theorem 16. The fundamental theorem of projectivity for a net of rationality on a line. If A, B, C, D are distinct points of a linear net of rationality, and A', B', C' are any three distinct points of another or the same linear net, then, for any projectivities giving A, B, C, D projective with A', B', C', D', and A, B, C, D projective with A', B', C', D1', we have D' equal to D1'. Assumptions A and E. Proof: if pi and pi1 are respectively two projectivities of the theorem, the projectivity pi1 pi inverse leaves A', B', C' fixed and transforms D' into D1'. Since D' is harmonically related to A', B', C' by Theorem 7, the theorem follows from the lemma. This theorem gives the answer to the question proposed in its relation to the transformation of the points of a linear net. The corresponding proposition for all points of a line, i.e., the proposition obtained from the last theorem by replacing linear net by line, cannot be proved without the use of one or more additional assumptions, chiefly Section 50, Chapter 6. We have seen that it is equivalent to the proposition, if a projectivity leaves 3 points of a line invariant, it leaves every point of the line invariant. Later, by means of a discussion of order and continuity, terms as yet undefined, we shall prove this proposition. This discussion of order and continuity is, however, somewhat tedious and more difficult than the rest of our subject, and besides, the theorem in question is true in spaces where order and continuity do not exist. Footnote: different, of course, from ordinary space, rational spaces, chiefly page 98 and the next footnote, are examples in which continuity does not exist. Finite spaces, of which examples are given in the introduction, section 2, are spaces in which neither order nor continuity exist. It has therefore seemed desirable to give some of the results of this theorem before giving its proof in terms of order and continuity. To this end, we introduce here the following provisional assumption of projectivity, which will later be proved as a consequence of the order and continuity assumptions which will replace it. This provisional assumption may take any one of several forms. We choose the following as leading most directly to the desired theorem. P. An assumption of projectivity. If a projectivity leaves each of three distinct points of a line invariant, it leaves every point of the line invariant. Footnote: we have seen in the lemma of the preceding theorem that the projectivity described in this assumption leaves invariant every point of the net of rationality defined by the three given points. The assumption simply states that if all the points of a linear net remain invariant under a projective transformations, then all the points of a line containing this net must also remain invariant. It will be shown later that the ordinary geometry of points of a linear net of rationality on a line correspond to the points of the line whose coordinates, when represented analytically, are rational numbers. This consideration should make the last assumption almost, if not quite, as intuitionally acceptable as the previous assumptions A and E. We should note first that the plane and the space duals of this assumption are immediate consequences of the assumption. The principle of duality, therefore, is still valid after our set of assumptions has been enlarged by the addition of assumption P. We have Theorem 17. The fundamental theorem of projective geometry. If 1, 2, 3, 4 are any four elements of a one-dimensional primitive form, and 1', 2', 3' are any three elements of another or the same one-dimensional primitive form, then for any projectivities giving 1, 2, 3, 4 projective with 1', 2', 3', 4', and 1, 2, 3, 4 projective with 1', 2', 3', 4 sub 1', we have 4' equal to 4 sub 1'. Assumptions A, E, and P. Footnote: on this theorem and related questions, there is an extensive literature to which references can be found in the Encyclopedia articles on projective geometry and foundations of geometry. It is associated with the names of von Stout, Klein, Hilbert, chiefly, also, section 50, chapter 6. Proof. The proof is the same under the principle of duality as that of Theorem 16. Assumption P replacing the previous lemma. This theorem may also be stated as follows. A projectivity between one-dimensional primitive forms is uniquely determined when three pairs of homologous elements are given. Assumptions A, E, and P. Corollary: if two pencils of points on different lines are projective and have a self-corresponding point, they are perspective. Assumptions A, E, and P. Proof. For if O is the self-corresponding point and AA' and BB' are any two pairs of homologous points distinct from O, the perspectivity whose center is the intersection of the lines AA', BB' is a projectivity between the two lines which has the three pairs of homologous points OO, AA', BB', which must be the projectivity of the corollary by virtue of the last theorem. The corresponding theorems for two- and three-dimensional forms are now readily derived. We note first, as a lemma, the propositions in a plane and in space corresponding to assumption P. Lemma 2. A projective transformation which leaves invariant each set of 4 points of a plane, no three of which belong to the same line, leaves invariant every point of the plane. A projective transformation which leaves invariant each set of 5 points of space, no 4 of which belong to the same plane, leaves invariant every point of space. Assumptions A, E, and P. Proof. If A, B, C, D are 4 points of a plane, no 3 of which are collinear, a projective transformation leaving each of them invariant must also leave the intersection O of the lines A, B, C, D invariant. By assumption P, it then leaves every point of each of the lines A, B, C, D invariant. Any line of the plane which meets the lines A, B, and C, D in two distinct points is therefore invariant, as well as the intersection of any two such lines. but any point of the plane may be determined as the intersection of two such lines. The proof for the case of projective transformation leaving invariant 5 points, no 4 of which are in the same plane, is entirely similar. The existence of perspective collineations show that the condition that no 3 or 4 of the points shall be on the same line or plane is essential. Theorem 18. A projective collineation between two planes or within a single plane is uniquely determined when 4 pairs of homologous points are given, provided no 3 of either set of 4 points are collinear. Assumptions A, E, and P. Footnote. We confine the statement to the case of the collineation for the sake of simplicity of enunciation. Projective transformations, which are not collineations, will be discussed in detail later, at which time attention will be called explicitly to the fundamental theorem. Proof. Suppose that there were two collineations, pi and pi1, having the given pairs of homologous points. The collineation pi1 pi inverse is then, by the lemma, the identical collineation in one of the planes. This gives at once that pi1 is equal to pi, contrary to the hypothesis. By precisely similar reasoning, we have Theorem 19. A projective collineation in space is uniquely determined when 5 pairs of homologous points are given, provided no 4 of either set of 5 points are in the same plane. Assumptions A, E, and P. The fundamental theorem deserves its name not only because so large a part of projective geometry is logically connected with it, but also because it is used explicitly in so many arguments. It is indeed possible to announce a general course of procedure that appears in the solution of most linear problems, i.e., problems which depend on constructions involving points, lines, and planes only. If it is desired to prove that certain 3 lines L1, L2, L3 pass through a point, find 2 other lines M1 and M2 such that the 4 points M1, L1, M1, L2, M1, L3, M1, M2 may be shown to be projective with the 4 points M2, L1, M2, L2, M2, L3, M2, M1, respectively. Then, since in this projectivity the point M1, M2 is self-corresponding, the 3 lines L1, L2, L3 joining corresponding points are concurrent by Theorem 17, corollary. The dual of this method appears when 3 points are to be shown collinear. This method may be called the principle of projectivity, and it takes its place beside the principle of duality as one of the most powerful instruments of projective geometry. The theorems of the next section may be regarded as illustrations of this principle. They are all propositions from which the principle of projectivity could be derived, i.e., they are propositions which might be chosen to replace assumption P. We have already said that ordinary real or complex space is a space in which assumption P is valid. Any such space we call a properly projective space. It will appear in Chapter 6 that there exist spaces in which this assumption is not valid. Such a space, i.e., a space satisfying assumptions A and E but not P, we will call an improperly projective space. From Theorem 15, Corollary 1, and Lemma 1, we then have Theorem 20. A net of rationality in space is a properly projective space. Assumptions A and E. It should here be noted that if we added to our list of assumptions A and E another assumption of closure to the effect that all points of space belong to the same net of rationality, we should obtain a space in which all our previous theorems are valid, including the fundamental theorem, without using assumption P. Such a space may be called a rational space. In general, it is clear that any complete 5-point in any properly or improperly projective space determines a subspace which is rational, and therefore properly projective.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.